Okay, we can we can start. So we restart from where we closed on Tuesday with the idea of the put call parity, where we have seen that if we buy a call option and sell the future, we are obtaining a put option. And we have also seen that the price at which this synthetic, this recreated put option can be obtained is actually 148, which is the same price at which the put option is trading on the market. We were starting from the 109 call option with a premium of 263, and the corresponding put option is worth exactly 148. Now, the first extra step is understanding that if the price of the put option on the market, so the number that I had here, were anyway different from 148, which is the price at which I can recreate the put option in this way, there will be a chance for an arbitrage. So example number one, imagine the put option strike 109, we're trading at 1.50. If it were trading at 1.50, and I know that I can build a long put option by buying the 109 call and selling the future, I could buy the call, sell the future, and sell the put option at 1.50. Because the put option would be overvalued, trading at 150, as opposed to what is going to be the cost of recreating the put option, which is 148. Okay? Now, imagine, as a second possible case, what would happen if the put 109 were trading at 1.46, so below the 148 that I obtained here. In this case, the price of the put option on the market would be relatively cheaper. Here, I'm assuming for the moment that there are no transaction costs whatsoever. If we had no transaction costs whatsoever, what we could do? It would be to invert the strategy. So intuitively, while if you buy the 109 call at 263 and sell the future, you get a long put option. If instead you sell the call and buy the future, you're going to get a short put option. It would be equivalent to selling a put option at 148. And you could complete the arbitrage by buying the same put option at 146. Is that okay? Intuitively, if you did that, imagine that you combine selling a synthetic, so a recreated put at 148, plus you combine that with buying a straight put, the one that you find on the market, at 146, you would be in this kind of situation at maturity. On one hand, you are selling a put option in this way with a profit, sorry, with a premium of 148. On the other hand, you are buying a put option where you just pay 146. If you think about it, the combination of the two is that independently on what is going to be the final value of the future, you just make a profit of 0.02. You have no exposure at all in this case. Have I been clear? You end up with a certain profit for your arbitrage. Now, what we have been seeing today as a consequence is that the put call parity not only tells me that if I have a long call plus a short future, this is equivalent to a long put. This is the case that we first considered in our final minutes of Tuesday's class. But of course, if I invert the strategy, a short call plus a long future can be considered equivalent to a short put. If you want, this is as if we had an equation where first line we write x plus y is equal to z, and then we rewrite it saying that minus x minus y is equal to minus z. Is that okay? But similar to any of these equations, you can also play a lot with the terms and bring in one term from one of the different sides of the equation, changing the sign. So x plus y equal to z can be rewritten as x is equal to z minus y. And as a consequence, for instance, you can also say that if you have a short call plus a long put, which is what I obtain if I take the short put on the other side, this must be equal to what? To the long future changed by sign, so it must be a short future. And by inverting the terms that I have here, a long call plus a short put should be equivalent to a long future. Let us remind, which is crucial, that here I'm not writing every time in the first and the second term, but I'm always talking about the call and the put option with the same strike, okay? If they didn't have the same strike, this would be no longer true. But for instance, just as a quick check that what we are writing is not something nonsense, if you think about this case, think quickly about what is going to be the graph of the P&L. If you have a long call, you have this profile, okay? If you have a short put with the same strike, you have this profile. It is pretty intuitive that if you sum them up, you get this, okay? Which is exactly a long future in terms of P&L. Have I been clear? Incidentally, it's not a waste of time to try to play a bit by reconstructing the graphs, even with the set of premia that I gave you, just to see that this is what is happening. And finally, there are also other ways of looking at that. If, for instance, we have a short put plus a short future, consider the first equation. I've taken the long put on the first member, changing the sign so it becomes a short put, and I left the short future. This must be equal to what? You have the long call going on the other side, so it's going to become a short call, and specularly, a long put plus a long future must be equivalent to a long call, okay? There are no more ways to see the story. We are done. But the point that I wanted to clarify when I said that we're going to see in a more generalized manner the put-call parity is that it is not just a combination of call plus a riskless investment equal to the put plus a stock. But actually the key idea is that by combining one option with a short or long future position, you can transform it into the other one, essentially. And in a number of cases, as I'm going to show you later on, this can be used sometimes, very rarely, to make up a full arbitrage and make money, sometimes more frequently, to take a long or a short call slash put at more convenient prices than what you could do if you just go and bought or sold the call or the put. Incidentally, in the case of options, European options on stocks, what would change here is that rather than having a short or a long future, you should have a long or a short forward. So you consider a forward sale or a forward purchase of the underlying, okay? That would be the way to change the position quickly. But now, let's make another step. The other step is understanding better from the point of view of the relationship between the prices that we must have between the call and the put price, what's actually happening. Because, of course, the put-call parity is forcing a given relationship between call and put prices. And I want to clarify better what's the intuition behind that. Now, let me ask for a second. We were considering earlier the 109 strike call and put, where we have seen that starting from the 2.63 109 call, we can build the 109 put, which must have a price of 148, okay? Remember that the June future price, so the future underlying these contracts, is trading at 110.15. The question that I'm asking you is simple. With a strike of 109, which option is in the money between the call and the put? Is 109 a good price to buy or a good price to sell if the market trades 110.15? Is a good price to buy. So the call option has some intrinsic value, okay? Which is the intrinsic value of the call option there? According to my definition of intrinsic value, which in this case would be the maximum between F minus K or 0. For the 109 call, which is this amount exactly? I can buy at 109 rather than 110.15, so it's 115, okay? Now, which is the difference between the two premia? It's exactly, if you look at it, it's exactly 115. Okay? Look at second case, which is easier. If you consider the 110 contract, which is formally the at the money because it's one which is closer, still with the future trading 110.15, one between the call and the put has a small amount of intrinsic value. Which option has a small amount of intrinsic value at 110? Again, the call option. Which is its intrinsic value? 15 cents. The difference, again, between the prices is 15 cents in favor of the call option. Okay? Third and final case, then potentially you can go on tonight with your parents and relatives all the night with all the prices in here. As I said, the crucial thing is having prices which close exactly in the same moment with super liquid market, otherwise this is not working. But if you take the 111 contract, at 111 is a good price to sell. So at 111, it is the put option being in the money, okay? Which would be the intrinsic value of the 111 put? Since I can sell 85 cents higher than the market, I would have 85 cents of intrinsic value. And if you see, the put option is trading exactly 0.85 larger than the call. Have I been clear? What is the intuition? The intuition is what? In terms of relationship between prices, the put-call parity is telling us a very simple story, which is the two options must have the same time value, and the difference between the two prices is that the option which is in the money should be worth more than the other one by its intrinsic value. That's the story at the end of the day. Let me be clearer. When you look at 111 call and put options, the total premium is 155 and 240 respectively. If you wanted to disentangle intrinsic value and time value, for the call option, it would be clearly 0, because clearly the option is not exercisable. You won't buy at 111 when the market trades 110.15. And so 155 is all represented by time value. For the put option, it would be 0.85, and the time value would be the difference, 240 minus 0.85, which again is 155. Now, why do we have the same time value? It's not for a random reason, but for something which is super understandable. Let us get back for a second to what lies behind the time value in our first explanation. I have a call option strike 111. If the future trades 110.15, I'm here, okay? The time value that this call option has to do with the chance of future exercise or with the chance of abandoning the contract. Has to do with the chance of potential future exercise. What is the time value pricing here? Is pricing there is neutral probability that the price can move from 110.15 to a value larger than 111. Is that okay? That's what lies behind the time value here, okay? Now let us consider the put option. In the put option strike 111, where this is the graph, at 110.15, the time value now is motivated by the chance of abandoning the contract. But for the put option, what would you need in order to abandon the contract? You should have the price moving from 110.15 to a price greater than 111. You are pricing the same event if you want. What lies behind the two time values is the probability that the price from 110.15 will move up than 111. Have I been clear? So that's the intuition and possibly a more general way to think about the put call parity. Clearly, one of the two options has to be in the money, the other is out, and the in the money option is worth more. How much? Exactly its intrinsic value. That's it. So incidentally, if you have two perfectly at the money option, the price has to be identical. Okay? So let me formalize it better. From the point of view of these options on Bund futures, the put call parity is super simple. Call minus put has to be equal to F minus K. And in this contract is super simple also because we do not have discounting. So the difference between the two premia is equal to F minus K. You can think about it in two cases. When F minus K is positive, when the future trades above the strike, which option is in the money, the call or the put? When the future is higher than the strike, it's the call option being in the money, okay? So you have a strike of 110 and the future trades 112, the call option would be in the money by 2. So if F minus K is positive, then the call is in the money and Chi minus P has to be positive, the call is worth more than the put. If instead F minus K is negative, both terms have to be negative because the put is in the money and must be worth more than the call. Have I been clear? All right. One key concern that I have with what I've just written is the following, that for your personal safety on the work and my personal safety on the work, I want to make sure there is no risk whatsoever that we misunderstand what we've written. Because here it's important, I don't want any of you, including people at home or hearing these in a registered form, to go and say to other friends or relatives, look, we found up the put call parity for American options. This could imply my firing. The reason is simple. There is no put call parity for American options in general. Put call parity stands for European options. For American options, you tend to have an inequality, not an equation. Why? Because either the call or the put can be early exercised, typically, and as a consequence, one of the two options is worth more than the European. So what you're going to have are inequalities. The reason why here we have options on Bund futures, which are American options with a put call parity and an equation, is only because they are fake American options, as I described in the first class. They are American options, but they are priced as European ones because early exercise is essentially never convenient. So it's a very, very specific, super strange case. And please do not say this is the put call parity for American options. That's the put call parity for options on Bund futures, because they are not truly American options. Otherwise, for all American options, you only have an inequality. Okay? But now, with the intuition that we got that the difference between the two premia must lie in the intrinsic value, if we what is going to be true for options, European options on stocks? If you remember, my modified version of intrinsic value for these options were respectively equal to the discounted value of ST minus K and the maximum between this and 0 for call options. For the put option, it was simply the maximum between the discounted value of K minus ST. Okay? It's not super necessary to rewrite them. It's the formulas we had already on Tuesday when discussing the intrinsic value for these options. So, in general, to what is going to be equal call minus put? Call minus put is going to be positive when the call option is in the money. Okay? So, the difference between the two is simply the discounted value of ST minus K, with the understanding that if ST minus K is positive, it's the call being in the money, and then the call is worth more than the put, okay? If K minus T minus ST is positive, so if ST minus K is negative, if you want, you can invert it and write P minus C is equal to the intrinsic value of the put. Is that okay? So here I've written the formula with call minus put for the general historical favor for call option as opposed to put options. In the Students Association, put option supporters among Bocconi students, you can rewrite it inverting the terms, which is totally fine. Okay? Now, one small extra. In the HAL textbook, in the part that you can read yourself easily and quickly, there are a lot of pages on that looking at what is the put call parity for options on stocks that pay no dividends, options on stocks that pay continuous dividend, options on stocks that pay discrete dividend, options on currencies, and you have 4 different formulas. My personal suggestion is just to remember this one, because this formula is correct for all of these cases. Just what is the difference is that you have a different ST. If you have an option on a stock, ST is S times C power RT. If you have an option on a stock with a discrete dividend, you have S minus I times C power RT. But if you write that in terms of the forward price, in these terms, it always works. Okay? And you have just one formula for all option types. For all option types with the premium paid in advance. Okay? With premium paid today, because this discounting comes because you are paying the premium today. Is this fine? So all the formulas there are variants of this. Incidentally, just 2 seconds, which could be useful, we can super easily reconcile this formula with the ones you had in the first semester when talking about the put call parity first. To my knowledge, if I'm not mistaken, you saw that by seeing that if you have a call option plus a riskless investment, that's producing the same result at maturity that the put option plus a stock, okay? How can we get there super quickly? If you have a stock with no dividends, then the forward price is simply S times E power RT, okay? What happens if I substitute this into ST in the formula? Very simply, I get that C minus P is equal to E power minus RT times S times C power RT minus K discounted. Super clearly, these two offset, and we can simply end up bringing K discounted at the first term, P at the second, and we have the put call parity in the way in which you probably have seen that in the first semester. Okay, That's one specific case, just the case in which you have no dividends. In my personal suggestion is keep in mind this formula, because independent on whether you have no dividends, one discrete dividend, 20 discrete dividends, one continuous yield, it works all the same, just with a different ST inside, okay? All right. Now, an extra part which is slightly more complicated, but not too complicated at the end, is understanding what happens when you have transaction costs. Because I will not mention transaction costs systematically through the course, unfortunately I cannot, but as we did for the forward price, when I gave you the idea, look, not always you are able to make the full arbitrage of the cash and carry or the reverse cash and carry, but much more frequently, you might have chances to sell or buy forward at a better price using the no arbitrage relationship. The same thing holds for the put call parity. Consider this example. Imagine you have the future at 110.15, and imagine that when you consider options with a strike of 111, you have the following bid and ask prices. The call is quoting 153 bid, 157 ask. The put option is quoting 2.41 bid, and in terms of ask, it's quoting 2.45. What I'm going to show you is that in this case, there is a small mispricing relative between the call and the put, and the size of the mispricing is not sufficient to make it possible to go through the whole arbitrage with transaction cost and make money, but what implies is that if we want to take some position on the put, for instance, we can save money, okay? Or get a larger amount of money. First of all, in order to understand quickly and roughly which of the two is overvalued as opposed to the other, just consider one thing. If you have a strike of 111 and the future trades 110.15, which of the two options is in the money? The call or the put? The put option, okay. Which is the intrinsic value of the put option precisely? Strike 111 while the market is 110.15, it's 85 cents. So we would expect the put trading 85 cents higher than the call, okay? Now, if as a crude simplification, we look for a second at the mid-market price, so just a simple average between the bid and the ask, we get that the call option has a mid of 155, the put option has a mid of 243. This can be a super quick trick to understand out of the number of arbitrages you can try that some are a totally waste of time. So here what happens is that 155 plus 85 cents would be 240. If the mid of the put is 243, it means that the put is slightly overvalued, okay? So which is the only possible arbitrage that you can be making here? If the put is overvalued and symmetrically the call is undervalued, the arbitrage, if it is possible, we are going to check whether this is the case. Would imply what? If the put is overvalued, what we should do? Sell. If the call is undervalued, we should buy, okay? So two clear pieces of the potential arbitrage are going to be these two, okay? So we sell the put. At which price we sell the put given that we are not market makers? We sell at the bid or at the ask? We sell at the bid, okay? And therefore, we take 2.41. And we buy the call, but we buy it at the ask. So we have to pay 1.57, okay? Now, a point I decided to spend a few minutes making this example because once in which there was an exercise with this story, I thought it was not impossible to be made, but there was a small proportion, small but still too large for my taste as a professor, of people who concluded the arbitrage is possible because the difference between these two is positive, it's also a large profit. Of course, in an arbitrage, you can't expect to make so much money. So here there is something missing. What is the part that we are missing? First, if you sell the put and buy the call, you have not yet closed the arbitrage. Think about it. If you sell the call, sell the put and buy the call, you are summing up these two positions. These two positions together would be equivalent to what? To a long or a short future? A long future. So in order to close the arbitrage, you have to do what? You have to sell. Okay? So first part, the third component is sell the future. The second part of the story is that by selling the future, there is something more to be considered. Why? Because when you sell the put and buy the call strike 111, you are implicitly buying the future at 111, at the strike of the option. Okay? When you sell the future, at which price do you sell the future? At the market price. You can't sell to market participants, look, you know what? I bought the future at 111 in the put call parity, so please buy the future from me at 111. They say, we don't care. The price is 110.15. You sell it as at 110.15. Is that okay? So in the future part of the story, there is a loss which is equal to the difference between 110.15, which is the price at which you sell, minus 111, which is the strike of the two options, which is the price at which you implicitly buy. Have I been clear? Now, if you look at the difference between these two, the difference between these two is plus 84 cents, whereas this is minus 85 cents. Is that okay? What is the conclusion on the arbitrage? Can we make the arbitrage or not? The answer is no, okay? The overall result would be a loss, so arbitrage would be not feasible. Is this fine? All right. However, let's move further one way. We've seen that even when the arbitrage is not feasible, maybe those who want to take a directional position can still make money and do something better. Now, what happens here is that is the put or the call overvalued? Let's get back to the second 155 to 43. Which of the two options is overvalued? The difference between the premium should be 0.85, which is how much the put is in the money, and the difference is larger than that. So the put is overvalued. If the put is overvalued, what's the implication? That what can be possibly wrong is the case in which you want to buy the put. If you buy the put and pay directly the ask price for the put, maybe this is too much. And the alternative to buying the put directly would be what? Would be buying the call and selling the future, okay? Now, if you consider buying the call plus selling the future, the total cost you would face, here I'm going in a quicker manner. If you're not convinced, when tonight you're going to explain this at home to all your friends and followers, try to make the graph as we did on Tuesday. And in this way, it will be crystal clear. But the cost in that would be the cost of the ask price of the call, which is 157, to which we should add the 0.85, which is this 0.85, derive from the difference between the strike and the future, okay? Just as an intuition, if you make the graph, you surely tried this with friends a number of times since Tuesday, but if you remember, what we had here was the 115, which was exactly the difference between the future price and the strike. This was done with the strike of 109. If you do with 111, 111 is rightwards relative to 110.15, but you find the 0.85 exactly in the same manner. So this is going to be the sort of cost or profit that derives from the future. In any case, if you don't trust me, just redo the graph and you will see. The total of these two, the sum of these two, is equal to minus 2.42, which should be compared with what? If you wanted to buy a put option directly on the market, how much would you pay it? Exactly. You would pay 245, which is the ask put price. So based on that, you say, look, if I build my put option by buying the call and selling in the future, I get a better price. Is that okay? Now, as an extra exercise for your followers, super intuition, what would be interesting instead to do on the call side? The put option is overvalued, which means that the call option is undervalued. So if the call option is undervalued, the intuition is rather than selling at the bid option, at the bid price, the call option, if I wanted to sell the call option, it would be better to sell the put option and transform that into a call through the appropriate position on the future. Is that okay? And you can see that if you compare these two alternatives, the winning part would be to sell the put option and transform that into a sale of a call, rather than just getting 153 of the bid of the call, which is too little. Is that clear? So with this situation, for instance, the classical one that you can find in real life, in which the true arbitrage is unfeasible, but there are two guys, the one who wants to buy the put and the one who wants to sell the call, that based on this small mispricing and knowing put call parity can make a better deal than otherwise. Have I been clear? All right. Well, this closes the part on put call parity, but hopefully it was a bit more fun and various than you might have expected earlier, I would tend to guess. Now we are going to enter into American options. With American options, we have to make two steps. Step number one is understanding, which was 5.1 in my agenda, is understanding when is early exercise convenient. Why do we care? Because if we can rule out early exercise completely, then we don't need a specific model for American options, because the American option should be worth as much as the European. If instead, even in some cases, even rare, it is possible that early exercise can be convenient, this would imply that the American option should be worth something more than the European, and they cannot use Black-Scholes, which would just be a lower bound of the price for me. I have to do something else. All right, we are going to discuss three cases, and I'm going to tell you in advance what's going to happen. The first case that we are going to discuss is going to be a call on a non-dividend paying stock, and in this case, the answer to our question is, when is early exercise convenient? Answer, never. So for a call on a non-dividend paying stock, the implication is that the American option is worth as much as the European. Second case, call on a stock with dividends, and here the answer is maybe. So we do not say that whenever there are dividends, it's convenient to early exercise, but we're going to see that if dividends are sufficiently not too trivial, it can be, with the sufficient level of the dividend, that early exercise becomes convenient. As a consequence, American option may be worth more. Let's say generally is worth more if there are at least a few cases in which early exercise becomes convenient. The third case is the put option. Here, even if I have no dividends, in both cases, and with the put option, the answer would be again, maybe. We cannot rule out early exercise, and so in general, the American option is worth more than the European. Okay? It's generally worth more. Let's say greater or equal, but most of the times is greater. Okay? Now, one point that I would, at the end, clarify. This is the typical structure also of how it is explained in textbooks. There is a big point of attention, a big caveat in Latin, which is one key assumption that I would point out your attention to at the end. So we are getting back here because that's important. Now, let me start from the first case, so a call on a non-dividend paying stock. How can we show that it is never convenient to early exercise? The idea is that there is something better to be done. And in order to clarify the story, I prefer to work with a numerical model example combined with theory altogether. So let's say we have an American call, strike 38 on a stock with a spot price equal to 40. And say that the maturity is, say, 0.5 years, and the risk-free rate is 2%. We are going to compare two strategies where I'm dividing the space on my sheet in an absolutely unequal way, because the first strategy is super simple, the second is a bit more complicated. Strategy number one is simply early exercise. How much money can I get by early exercising the option? In general, if I have a strike K and a spot price S, of course, the problem comes only when it is exercisable, so when S is larger than K, what I can get is simply S minus K, okay? In my example, just to keep numbers together with formulas, if I have K which is 38 and the spot which is 40, what I could get would be 2, okay? So I can get 2 immediately by exercising. Fine. What is the potential alternative? The potential alternative is to keep the option alive and sell forward the stock. The idea is if the spot price is high, the forward price would be high as well, and I can keep until maturity and see what happens. That's the intuition. Let's be more precise. So strategy 2 is keep the option alive plus sell forward. Now, what is going to be the forward price? The forward price, in this case, would simply be S0 times C power RT. Here, I've used on purpose exactly the same numerical example that we used already when talking about the intrinsic value. So if you have a 2% rate, 0.5 here, and S is 40, you end up having 40.40, okay? Of course, forward prices can in general have also different numbers, but to keep things simple, exactly using the same numeric example as we had on Tuesday. Now, the problem is that in understanding what is happening here, we have to distinguish two cases, however, because I have sold forward at a certain price, but I don't know at which price I would buy the stock. And this depends on whether I exercise the call option or not. which depends in turn on whether the final price is larger or not than the strike. So we have to distinguish two cases. The first case is the one in which the final price at maturity is larger or equal than K. Whereas the second case, to be, is the case in which the final price is strictly smaller relative to the strike price. Okay? Before we enter into the details of what happens in case 2A to B, let me give you the broad intuition. Here what's going to happen is that we are going to prove that early exercise is never convenient, because even if we have two possible results from strategy 2, even if we take the lowest of the two, this is going to be better than early exercise. So the idea is, here are two possible outcomes. If I see that the lowest of the two is better than early exercise, then strategy 2 in any case dominates strategy 1. And so strategy 1 will never be performed. That's the name of the game. Okay? So, first part, what happens in case 2A? First, I have the profits from the forward sale. Sorry, the profits, the inflow from the forward sale. And here I find it useful to write both the formula and the number. So in formula, what I get is plus ST. In number, I'm getting plus 40.40. Okay? But in order to deliver the stock, I have to buy that somehow. In this case, would I exercise the call or would I buy the stock on the market? If the final price is greater than 38, say it's 41, do you buy the stock at 41 or do you exercise the call and pay 38? It's pretty clear. Here we exercise the call option, okay? So the second part is that we exercise the call, so we pay K. In numbers, we pay 38, okay? So the result here is ST minus K, or in the numerical example, 2.40. What happens instead in case 2B? First, again, I have the forward sale, which is the same. This doesn't change, so I get plus ST, or in numbers, I get 40.40. Then, what would happen from the point of view of purchasing the stock? Imagine, for instance, that, just to make a numerical example, that the final price is, say, 36. You have the chance between buying the stock spot at 36 or exercising the call at 38. Clearly, here we do not exercise, and we buy the stock spot on the market, okay? So what we do is that we buy spot, we only pay as final. In the numerical example, we only pay 36, okay? So the result that we have here is ST minus S final, which is strictly larger than ST minus K. As we can also see from the numerical example, we are making 4.40 rather than 2.40, okay? Now, in order to see which is winning between strategy 1 and strategy 2, we have to do two final steps, which is taking the lowest of the two possible values of the outcome of strategy 2, which is ST minus K, and second, consider one thing, which is, while S minus K is obtained today, ST minus K is not obtained today, it's obtained at maturity. So I have to take the present value of this. Is that okay? So what I calculate here is the present value of the minimum profit, which is e power minus RT of the minimum profit, where the minimum profit is ST minus K, okay? Now, if we were looking at the numerical example, and if you want to explain with the numbers first when talking at home tonight, you could ask your relatives whether if they discount 2.40 for just 6 months with the just 2% rate, this is going to be more or less than 2. Probably if they've done a lot of discounting by mind with continuous compounding even in the first semester, most would guess that it's more than 2. If you discount just for 6 months, just the 2% is going to be around 238 or something, okay? But let's use the formula because this is clearer. How can I show that this is more than what I get from strategy 1? Because if I substitute in ST the formula for ST, this is equivalent to write S minus K discounted, okay? The first term, E minus RT times ST is simply S, okay? So what we are comparing is a case in which you get S minus the full strike compared with getting S minus the strike discounted, where intuitively the second amount is larger. Have I been clear? So what we find out from here is that given that even if we take the minimum of the two scenarios and we discount it, that's more than what we get by early exercise. Early exercise would never be convenient, and you can rule out that completely. Have I been clear? That's the point. All right, second and quicker case. The second and quicker case is the case in which you have dividends. So to clarify the story in terms of calendar, you have the maturity T for which is the maturity of the option. You have time 0, which is today, and in between, at the date T1, there is the dividend payment. And clearly, if you make the strategy in which you keep the option until maturity, and if you exercise only at maturity, it means that the dividends are lost. You get the dividends only if you exercise before the dividend payments, so that when the dividends are paid, the stock is in your portfolio, okay? Intuitively, the point is that if the dividends are trivial, you still don't exercise, but if the dividends are large enough, it might become convenient. In terms of super simple intuition, in numbers here we were comparing 2 with 238. If you have a dividend which is 0.70, maybe early exercise sounds reasonable, okay? But let's take again the formulas here, and let us be more refined. If you add dividends, you could rerun this example in the formula side exactly the same way, with only one difference. That is, when you get here, if you have dividends, ST is not the same. So let me jump back. You have to compare S minus K on one hand, and on the other hand, e power minus RT of ST minus K. But if there are dividends, ST is equal to S minus the present value of the dividend times e power RT, okay? If we substitute these ST in the formula, what we get is S minus I minus K discounted. And this minus I was not present in the case before. Is that okay? Now, while if you didn't have minus I, you would know that the second term is larger than the first one. If you have a minus I which is sufficiently large, this is no longer the case. Have I been clear? So for a dividend that comes sufficiently early and sufficiently big, then potentially your exercise may become convenient. Have I been clear? That's why we cannot rule out that on a general basis. Third case, put option. Consider a put option where we take an American put option, assuming, for instance, to have a strike of 42, and again, we have the same stock as before, with spot price of 40, R is 2%, time is 0.5, and the forward price is 40.40. I'm going a bit quicker because it's the same story, just slightly changed because it's a put option. So even here, what we do, first we see the first strategy, which is early exercise. Where what I can get today is K minus S. Because clearly I sell at K while I buy the stock at S, okay? In this numerical example, again, it would be 2 because I have a strike of 42, okay? What is going to be the second strategy? It would be keep the option alive plus what? In the previous case, I was keeping the call option alive and selling forward. Here I would keep the put option alive and I would buy forward, clearly. Now, let us see what happens in the two cases, where again, the first one is the one in which the option will be exercised, which means the case in which the final price is equal or smaller relative to the strike. And so the right thing is to exercise the option. Instead, the second case is the one in which the final price is strictly larger than the strike, okay? Example, let's say we have a final price equal to 45. Let us calculate again what is happening. In both cases, I have the forward purchase. So I pay ST. In numbers, I'm paying 40.40. I'm already writing it twice because also this happens in scenario 2B. Now, let us consider in scenario 2A in which way I sell the stock that I've purchased. If the final price is lower than 42, say it's 40, would I exercise the put option or sell it on the market? I would exercise the put option, okay? So in this case, I exercise the put, and I would get K, which in numbers would be 42, okay? So what I get is K minus ST, which in numbers is 1.60. Have I been clear so far? All right. The reason why I use also numbers, over the years I learned to use also numbers, not just the formula, is that, for instance, here it's going to be tremendously clear, even if we have not done yet part 2B, whether it is possible that strategy 2 wins over strategy 1. Based on your ability in discounted with continuous rates, if you have 1.60 discounted, is going to be more or less than 2? Any guess? Probably most of your audience tonight is going to agree that this is less than 2, okay? So it's pretty evident just from here that strategy 2 is not winning systematically, okay? Yet we do quickly also case 2B, but super quickly. Here, if we were in case 2B, rather than selling with the put option, we would sell spot. So we would get S final. If the final price, for instance, were 45, I would get 45, which means what? From a formula standpoint, I would get S final minus ST, which is larger than K minus ST. So K minus ST would be my minimum profit here to be considered, okay? From the point of view of the numbers, what I get is 460. Again, why I use also the numbers? Also for a reason here, because one potential mistake would be to say, look, after I've seen case 2A, I end up to the conclusion that since strategy 2 never dominates, it's always optimal to early exercise. No, it's not necessarily optimal to early exercise, because in strategy 2, sometimes it can go worse when I finish in 2A, but sometimes it can go even better, as we see in 2B. 4.60 discounted is clearly a lot more than 2. Is that okay? So the fact that early exercise cannot be ruled out doesn't mean it's done systematically every time the option is in the money. It's a completely different story, okay? Now, from the point of view of checking whether strategy 2 is dominating strategy 1, again, the last step would be, let us take the present value of the minimum profit, which is going to be the discounted value of K minus ST. Again, if I substitute ST, saying that it is S times C power RT, this ends up being the discounted value of the strike minus the stock price. And with this comparison, I finally conclude my fascinating proof saying, look, in this case, I cannot say that strategy 2 always dominates strategy 1, because taking K discounted is taking less than K, okay? So this will be the final step in which I say, for put options, I cannot rule out early exercise, which doesn't mean I do early exercise whenever I can, as we've said, because it depends on whether I think it's more reasonable to find out myself in strategy 2A or case 2A or case 2B. Is that okay? A minor note, this is not crucial, but a minor note in terms of intuition. If you see what is typically written on put options, which is totally correct, there is something that tells you what is making early exercise more likely. And just to be super simplifying, imagine that here, rather than having the stock price at 40 with a strike at 42, you had the spot price at 20, okay? Meaning that the option would be incredibly more in the money than it is now. Which would be the chances that you can find yourself in scenario 2B at the end? For scenario 2B, you must have the final price larger than the strike. If the price is 40 and the strike is 42, you still have a lot of chances. But if the spot price is 20 and the strike is 42, there are basically no chances whatsoever. Is that okay? So intuitively, the more you are in the money and the more you are close to maturity, which means that you have fewer chances that the price from below the strike comes higher than the strike, and the more likely is early exercise. When you have early exercise, it tends to be concentrated for very deep in the money option, and especially over the last periods. Is that okay? That's the intuition. Now, so these should explain the usual textbook story, which is here. So we saw, first case, call on non-dividend paying stock, I never early exercise. If I have dividends on the call, maybe, on the put option, maybe, with the consequence of when American option is worth more than the put. Which is the key caveat, a key assumption here on which I would like to draw your attention, is that the key assumption here is that rates are positive. That's the key story behind all the reasoning we made. Why? For a very simple reason. If rates are negative, are you still sure that K discounted is less than K? It's the other way around, okay? So if rates are negative, the conclusions are just inverted. In the case of the call, you have a situation in which you cannot rule out early exercise, whereas instead, in the case of a put, you can, because K discounted is larger than K. Have I been clear? This is slightly relevant because you had tons of people formed only with lives of positive rates where all the models only were allowed to have positive rates, and then suddenly in the last years we had negative rates. And what was the conventional wisdom in this case is just inverted. Is that okay? So the textbook story is the one, but keep in mind that it depends on rate level significantly, exactly this proof. Have I been clear? All right. Now, the next and final step for today is, when now I have options that I have to evaluate in some more specific way because, for instance, early exercise is possible, what do I do? And the typical answer is I use the binomial model. So I'm going to super quickly review the binomial model, but super quickly. We are going to finish the binomial model by the end of this class. So I take profit of what you've done in the first semester, just to give you the intuition of what is the small change when I use that for American options. In the binomial model, what you do? Essentially, you start having an initial price of the stock, and you define a process of evolution of the price of the stock. So for instance, let's say that every period, the stock can go up by an amount U or go down by an amount D. And for instance, if I just draw a 2-period binomial tree, after 2 periods, the price can go up a second time and having a U squared S, or go down or down up and having a price equal to U times D times S, or go down twice and having D squared S, okay? Example, just to put numbers in it for a second, imagine I start from 100 and given a certain U and D, I can end up saying the price here is 104.16, here is 100, and here is 87 something, okay? Then imagine you want to price a call option, strike 9, okay? How can you do after you add your assumption on the tree? You start from the final value, because you say, given the price of the underlying, I can tell easily what's going to be the value of the option at maturity. It's going to be 50.16 if the final price is 104.16. If the final price of the underlying is 100 and the strike is 99, I exercise and I get 1. If the final price is below 99, I get 0. Okay? And then the binomial model works with backward induction. So what you do is that you go back 1 period and you take the value here. So let's say that f is the value of the derivative. So FUD stands for the value after 2 up moves. FUU. FUD is one after 1 up and 1 down move. And FDD is the value after 2 down moves. If you want to derive which is the value here, FU, can be derived by discounting back by 1 period, taking into account the risk neutral probabilities of the movements up and down. So for instance, FU would be equal to e power minus R times delta T, where delta T is not the maturity of the option. Delta T is the length of one node, okay? Multiplied by P times FUU plus 1 minus P times FUD. You cannot see because it is frozen. Wow, let me see whether I can solve it somehow. I can just try to block the sharing and then re-put the sharing. That's the best thing I can do. Wow. Can you see now? Okay. So you followed until the strike of the call. So until I was mentioning, the strike was 99. So as a consequence, first, let me recap. Sorry for the people in the classroom. So first you identify the payoffs at maturities, which are derived starting from the final price of the underlying in the node and the strike of the option, step number 1. And in this way, you get the column of the values at maturity, which I defined as FUU, FUD, FDD based on the number of up and D movements that you need to get there in terms of the price. Then you can derive with backward induction the value of the option 1 period earlier. So for instance, in order to calculate the value after an up move, you take the discounted value for 1 delta t period, delta t being the size, the distance between two prices, the size of one node, that is multiplied by the risk neutral probability of moving up times the value of the option in the up case, plus 1 minus p, the risk neutral probability of going down, times the value in the down case. Similarly, you derive an FD here, and in the same way, discounting back another period, you derive the initial value of the derivative as a discounted weighted average of FU and FD. That's how the binomial model works, okay? Now, incidentally, well, no, all right, I will add the incident in 2 seconds. The intuition is what happens here if you have an American option. In an American option, what you can do is early exercise. So the intuition is the following. When you are here in this node that we have seen, you're going to say FU is going to be the value of the option if you keep it alive for another period. But the alternative is early exercise. So you compare the value of the option kept alive another period with the value of early exercise in that node. And then you take whatever is greater. The idea is that whenever the greater value is the value of the option kept alive, you will not exercise and see what happens in the next period. If instead in a single node you find that its early exercise is the bigger one, then it means that in that node, if you were there, you would early exercise and terminate the contract, and this greater value would be the value of the American option. And then you move backward another period. Okay, so you check systematically in your backward induction whether in any node early exercise might be better. That's the story. All right, before running the example with the binomial model, just two small additions. The first one is U and D should be made in a way which match the volatility of the underlying. Intuitively, U and D are a measure of volatility. The larger is U and the smaller is D, the more volatile is the asset, okay? And typically, when, for instance, you try to use the binomial model to get the same numbers for Black-Scholes, there must be a linkage between U and D and the sigma you put into Black-Scholes. The typical linkage which is used is to set U equal to the exponential of sigma multiplied by the square root of delta t. Please attention to the fact that first is not sigma delta t, but sigma times the square root of delta t. And second, that delta t is the node, not the maturity of the option, okay? So the more nodes you make with the same maturity, the smaller is delta t. And the d, instead, is the exponential of minus sigma times the square root of delta t, which implies that when you have an up and down movement, you get to the same price as before, because U times D is 1, okay? So that's the typical setting that with a tremendously thick binomial model gives you the convergence with the Black-Scholes model using the same sigma. That's the story. Have I been clear? Second part of the story, which is something I should have done when discussing the risk factors, but I forgot, apologies, is to say better what my sigma is, what is the sigma we care about. Because when we have volatility, we can have in mind, sometimes without being clear with ourselves what we think about, 3 different ideas. One is historical volatility, one is expected volatility, and the other one is implied volatility. I'm going to clarify better what the third idea is, and this is the one we care about. Historical volatility is the volatility that I can measure in past data. So my sample of data, I can measure a volatility saying in the 2019-2020 daily volatility of the S&P 500 was 32%, okay? Expected volatility, or if you wish, forecast volatility, is an estimate that you can make on the future based on my subjective expectations, the magician, which is a friend of mine, my econometric model, depending on what I trust more, probably the third one, on what is going to be volatility in the future. But it's my however technical expectation. What we truly care about in option pricing is implied volatility. What's the idea? Now, if you want to make a price with Black-Scholes, you want to price an option with Black-Scholes model, you typically have a number of elements which are absolutely observable. That's the case for the spot price, the strike, time to maturity, and the risk-free rate. On this, there is no disagreement between parties, okay? However, the fifth element is the volatility from now to the end of the contract. And this is not observable. So whenever you want to use Black model for pricing, you have to put inside your sigma star, which is your estimate of volatility for the future, ideally. Let's say you think volatility is 20%, and conditional on 20% being the right volatility, Black-Scholes tells you, look, the premium for the option is, say, 250, okay? But this 250 is driven by the volatility you have put inside. If you use the different volatility, you will get a different premium, okay? So imagine that you price this option and you come up with the idea that the premium should be 250. Then you take a breath, go and say, which is the premium at which this option is trading on the market? And you see that the premium on the market is, say, 270. Does the difference between your estimated premium of 250 and the market premium of 270 mean that the market is overpricing necessarily? Not necessarily. There can be an alternative explanation, which is the market is using a different expectation of volatility relative to you. Is that okay? So in this case, what you do is the following. You use again the Black-Scholes model. You put again in the model as an input the data which are absolutely objective. So again, S, K, T, and R. You put as an input, not as an output, the premium which has been given by the market. And you use that to derive which volatility the market must have used in order to produce a 2.70 premium. Have I been clear? Incidentally, in order to produce a 2.70 premium, so a higher premium, would you need a higher or a lower volatility relative to 20%? Think about the graph that we made of the time value of the option and how it reacted to volatility. If you have higher volatility, the value of the option goes up or down? It goes up because time value increases. So in order to get a higher premium, here you would need a higher volatility, okay? Here you can't invert the Black-Scholes model. This is done by iteration until you find the right premium with the right number of decimal digits. But let's say that by iteration we need a 22% volatility, okay? This is what we call implied volatility. And what is driving closing prices on the market, which is what I eventually care about as a trader, is implied volatility. So what matters is which is the change in implied volatility, which is the average expectation of volatility of the market behind closing prices. Have I been clear? So that's the one we are going to use also, incidentally, in the binomial model to set the right U and D. Have I been clear? All right. So the final step for today is to look at one example of the binomial model just to clarify better what I just said on the usage of that in the case of American options. As I said at the beginning, I don't know if you were all connected, I apologize because I just uploaded that probably 2 minutes before today's session started. So this is available it has been available for the last hour on Blackboard. But here what we have is that we are considering a put option, an American put option with strike 98. Imagine you have the price of the underlying at 100, volatility is 10%, options maturity is 1/3 of a year, what many people would call 4 months, clearly. I have 4 intervals, which are 1 month each, 1/12 of a year. And the strike price is 98, and the short-term interest rate is 4%. And here I have all the parameters, UD, PN1 minus P, calculated based on these numbers. So for instance, this U is the exponential of 10% times the square root of 1/12, okay? Because delta T is 1 month out of 12, okay? Now, if I run my binomial model, the first thing I make, here I'm assuming to have a 5-period binomial model, this would be the path for the price of the underlying stock. And as in any binomial model, the first thing I can say is which is the value of the option at maturity. Here I have a put option strike 98, so 98 is here in terms of level relative to the different final prices. So for all the prices greater than 98, I won't exercise the put and I get 0. I only get a payoff in these 2 possible states of the world at maturity, okay? Now, starting from here, it's super simple to understand that when coming with backward induction, in all these nodes, I can only have zeros, okay? The first node, which is interesting to calculate, is this one, X1. If I had a European option, I would take the discounted value of P, this neutral probability, times 0, plus 1 minus P multiplied by 361. Since I have an American option, what I do is I calculate this value, but I compare it with early exercise. Okay? Let us see how it works. The value of the option, if kept alive, is precisely the discounted value for 1 period. So please note that here I'm discounting for delta T, which is the node, not clearly for the full T, obviously. Of P times 0 plus 1 minus P times 361, which happens to be 162. In order to calculate early exercise, I should consider that I can sell anytime at 98. And when I'm in X1, the corresponding price S is 97.15. Okay? So early exercise would be the strike price minus the price that I have in this node, which is 97.15. So if I were there, I could get 0.85. Have I been clear? What would be more convenient here? Clearly, keep the option alive, because the value is larger than 0.85. So if I ended up in X1, I would not early exercise. This allows me to write 162 here, which is the greater between the 2 values, and move me to considering what happens in X2. In X2, I do again the same thing. So I take P times the up value plus 1 minus P times the down value discounted. This is what I have here. And this ends up being 597. However, the spot price here is 91.70, which is particularly low. And as a consequence, if I were there, I could sell at 98, which is the strike, buy at 91.70, so I have a value which is 630, which is larger. So in the node X2, early exercise would prevail. Have I been clear? All right. Now there is the only thing to which it's important to keep attention, which is what happens when you are in X3. The potential mistake that some do is that in X3, they say, I have early exercise if the value of early exercise is larger than the value of the European option. This is wrong. What you have there is an American option. So what you should say is the comparison between the value of early exercise and the value of an American option kept alive in another period. What I mean is the following. When you calculate the value here, the value that you discount in the down move is 630. Because you take into account that if you go there, the option is not worth 597, which would be the value of the European. It's an American, so if you go there, it would be optimal to early exercise, and as a consequence, when moving backwards, you have to discount a larger value. Have I been clear? This is the only potential mistake that could be done. Again, here you compare the two, you see that what is larger is the value of the option kept alive, so you put 371 and you move backward. Now, I'm not poisoning you with all the different steps in the binomial tree. Of course, that's fine, you can have together if you want to go through the example. But what we can see is the following. Here we have the American put price tree compared with the European 98 put price tree. What we can see is the following, that just based on the fact that only here there is early exercise, clearly when I go backwards, all the values here are going to be larger than the corresponding values of the European. Okay? Whereas instead, in all the regions of the tree in which there is no early exercise, you have exactly the same values. In the region that I just highlighted with this badly handwritten cone, what is the difference is that in none of these nodes on the American side there is early exercise. And as a consequence, when you go backwards, you still find the same values for the American and the European option. But it's sufficient to get just one case, and just one is sufficient to have a larger value for the European option when you move backwards. Okay? Now, let me add just two simple things. Simple thing number one. When we were discussing early exercise for the American option earlier, I was saying that it was more likely to have early exercise when the option was deep in the money and close to maturity. Okay? Why? Because in the 2A, 2B situation, if you are deep in the money and close to maturity, it's much harder to be in case 2B, and so you probably conclude in a number of cases that taking the money soon is the best thing you can do. As you can see here, the only point in which in this binomial tree you have early exercise is precisely on the last node and with a tremendously low price of the underlying. Of course, depending on the parameters you set, it can be that you have exercises in multiple points. But what I mean is, if there is a region of early exercise, it must start from here and maybe be a bit larger. But you can't have early exercise randomly somewhere in the tree. If you have exercise, it's there, okay? First part of the story. Second part of the story, for people who would start now trading American options based on the binomial tree, it's important to take a sense of what is a reasonable number of nodes in a real-life model. Because, of course, in derivatives 1, probably, I suppose you've done at most 4 or 5 nodes, probably most of the time 2 or 3. In my exercises, there are 20. I'm kidding. In my exercises, there are typically 2 or 3 as well. In real life, the typical standard is having 100 nodes, and you never, ever use less than 30. Less than 30 is barbarian, okay? And typically, the standard is 100 or more. The problem is that if you have not a thin enough tree, clearly you would be underestimating the chances of exercise. And intuitively, it has also an impact on the option value, because in the less points you check early exercise, and the more you'll be potentially underestimating the American option value. Here, in the case in which early exercise is possible, it's super evident that the number of 3 is not irrelevant from the point of view of the value that you find out, okay? So 100 is the typical reasonable standard from which you start discussing. Of course, this is not something that you do in Excel. Usually, it's something which is in between your software, but it's important to keep in mind that the standard in that should be to have a sufficiently large number of nodes to have a decent valuation. Have I been clear? All right. If there are no Questions? I would stop here 1 minute earlier, but given that I've taken 1 minute extra multiple times, so I already apologize for that. It's not unfair. There are no questions from the audience at home as well? Understand? All right. So thank you. Next time is going to be on extensions of Black-Scholes. So in my agenda, we were up to point 5, which is American options. The next step is going to be extending Black-Scholes model for options on futures and on stock index futures. We are going to do that quickly and then start already on the part on Greeks. Incidentally, in the meantime, I might post something else during the weekend on the website, so give a look at it for potential slides for the next week. Thank you.